Good morning to my chemistry students. I am Mr. Reed. I teach chemistry at Chase Alternative Program, and this tutorial that you're about to see is a result of some problematic areas that I discovered in chemistry. One being the Lewis dot structures and the other being naming compounds. So what I would like to do, I would like to give you some information to help you name compounds as well as draw Lewis dot structures. So let's start with Lewis dot structures first. Lewis dot structures are important. The reason that we have them, they indicate the electrons that are important in bonding. And Lewis dot structures are actually just a simplified method or form of writing your compounds or writing your elements so that you can only see the bonding electrons. So let's look at some. I have some listed on the board, and you'll find out that I have various groups at the top. Lewis dot structures are easy to draw once you understand which groups your elements belong to. So we'll look at the representative group elements since they're the easiest to deal with. Let's look at group 1. You'll see a 1 here, and notice that I have lithium and sodium under group 1. Then I have other elements under group 5 and group 6 and group 7 and group 8 and so forth. The actual Lewis dot structures are represented by the group number. So all of those that are in group 1 actually have one electron in their valence shell. That would be the shell that has the highest number of electrons, or the electrons that are in the highest level. So if I'm drawing the Lewis dot structures, I want to look at the group that the element belongs to and simply draw that number of electrons. So all of these in group 1 would simply have one electron. And you're done. Now, we know that lithium has more than one electron totally, so does sodium. However, we only want the electrons in the valence shell, which would be the highest energy level shell for each element. So with all of these, they would have one electron. Similarly, the rest are very similar. You'd have those in group 5A, they would have 5 electrons. Those in group 6A would have 6. Those in 7 and those in 8 would have 7 and 8 electrons respectively. Now, how do you draw them? Well, since you look at your electron number, and that number would be such that it indicates which group it belongs to, you can easily draw the Lewis dot structures for any of the elements. Let's look at nitrogen. Nitrogen has 5 electrons in its valence shell, so does phosphorus. So let's draw nitrogen to see what happens. Since there are 5 electrons, the first 2 we can draw on any side of the element, and I'll choose the top. The others have to be drawn in a clockwise fashion. So we can draw them this way, 1, 2, 3, or you can draw them in a counterclockwise. And I chose to draw them counterclockwise because either way you'll end up with the same structure. Notice that there are 5 electrons, 1, 2, 3, 4, 5. Same with phosphorus. Put your first 2 on any side of your element. You could choose the top or the bottom or the sides, and then draw in a counterclockwise or clockwise form. 1, 2, 3, 4, 5. The electrons that are here, that you see that are loose, these are the ones that participate in bonding. So if I'm drawing a Lewis dot structure for any element, I'm only showing the valence electrons, the ones in the highest energy level. And the same thing would go for oxygen and sodium, or oxygen and fluorine and chlorine. They would have 6 electrons, and fluorine would have 7, neon and argon would have 8. And so if you notice, these Lewis dot structures can easily be drawn. And you can start with any 2 sides, 1, 2, 3, and then you go to this one. That gives you 6 electrons. Same with sulfur. They're in the same group, so that means that they have the same number of valence electrons. Now, that seems simple, and that should be the case when you draw Lewis dot structures. Make sure you look at the group number, and the group number will indicate how many electrons should be surrounding your element. If it's in group number 8, I should have 8 electrons surrounding. There are some exceptions. One would be helium. Helium is a gas that's in the noble gas column, but it only has 2 electrons, and that's because it only has 1 orbital, so it only needs 2 electrons to be considered stable. All of the others in this group would have 8. Even though they have more than 8, we only show the ones that are most important in bonding. Now, if that's the case, when we draw Lewis dot structures, we can now figure out how to name compounds, because it's our Lewis dot structures that indicate to us the types of compounds that we can form. That's because these electrons that are free to bond, they can bond to other electrons or with other electrons, and you can form a compound. So how would we name compounds? Well, let's use some of the things that we've drawn as Lewis dot structures. So let's look at some of these. I'll put the fluorine here so that at least we'll know what these are. And of course, remember we said they would have 7 electrons. Now, if we're going to name compounds, which I saw where some students had problems, and I can understand why, we first have to indicate whether or not our compound is ionic or covalent. If we figure out whether or not our compound is ionic or covalent, it will be easier to name. An ionic compound should have a metal and a nonmetal. And the metal always comes first. So let's look at ionic first. If there's a metal present and a non-metal present, then we know that it's an ionic compound and we can name it as such. Ionic compounds do not have prefixes before or after their particular name. So that means that when we deal with an ionic compound, we don't have to worry about numerical prefixes such as mono or di or tri or bi or tetra. We can simply name the first element the way it should be named and then add IDE to the second portion basically, and you'll be able to name your basic ionic compounds. So let's choose one. We'll look at sodium, and we're going to combine it with chlorine. And we're going to form an ionic compound with these two because one is a metal and one is a nonmetal. Sodium is our metal. Chlorine is our nonmetal. And notice they can bond. There's 1 electron here. There are 7 electrons here. And what will occur is so that each shell is filled, this electron will be transferred over to the chlorine. And that means that chlorine now has a full shell of electrons, and so now does sodium. It now has 8 electrons in its highest level because we just gave up 1. So let's name this compound to see what it would be named. We cannot name it sodium chlorine. That would be improper. So what we'll do, we'll name the metal first, the way it would be normally named. That would be sodium. But we're going to add and change the ending to chlorine to chloride. Notice all I did was change the chlorine, INE, to IDE. And when you name your ionic compounds, you will find out that the second portion will change from INE to IDE. Now that seems very simple, which it is. So if I can identify my compound as ionic, then I know that I can name the first portion, which is a metal, and name it exactly the way the element looks. I didn't change sodium at all. And I can add the other portion, which is a non-metal. And I only change the ending, which would be INE to IDE. So when we name ionic compounds, we simply name the metal first and then the nonmetal. Now, what if we have a compound that's not ionic? Well, that helps us to understand how we can name the compound. If I know that my compound is not ionic, it must be covalent. So let's look at some of those that we can perhaps name. So let's look at phosphorus, which we just drew the structure here, and oxygen. That can form a compound. And if it's not ionic, then it must be covalent. A covalent compound has 2 nonmetals as its components. And those 2 components you should know because they would not be in the metal category. So if you can identify your compound as covalent, then you should have both nonmetals, phosphorus and oxygen. So why don't we name these 2 and see what we can come up with. What if we had E4O6? Now with your covalent compounds, you will use prefixes in order to name your compounds. So this 4 and this 6, those 2 numbers, I have to use the prefixes, the Greek prefixes that represent them. So for 4 it would be tetra, for 6 it would be hexa, and I'll simply keep the element name. Now I will change the oxygen to oxide at the end. So this would be tetra phosphorus. Notice I didn't change the phosphorus. Hexaoxide. And the reason it's hexaoxide is because there are 6 of these atoms that you see present, and the 6 means hexa. Hexaoxide, tetra, 4, hexa, 6. Now, the only way I would know to do this and to use the prefixes, I would have to know that this is a covalent compound. Otherwise, it would seem as if I could name them just like ionic. But once I determine that this is a covalent compound, then I know I have to use prefixes. So that's how it would make it easier for you to differentiate as to which naming system you should use. If I first discover that it's an ionic compound, then I know that I don't have to use prefixes in my name. If it's a covalent compound, I do. So when we're naming compounds, first determine whether or not your compound is ionic or covalent. Ionic compounds always have a metal and a nonmetal. Your covalent compounds normally have 2 nonmetals. So as soon as I see 2 nonmetals, I know that I'm dealing with a covalent compound. If I see a metal and a nonmetal or some ions, then I'm dealing with what's considered an ionic compound, and that gives me the basis for my naming system. So those students who were confused with naming compounds or drawing Lewis dot structures, here's a tutorial to help you clarify in those areas in which you were confused. And hopefully, by using the tutorial, you'll be able to more easily draw Lewis dot structures and also name ionic and covalent compounds. I hope this session was helpful to you so that way you can do extremely well in that subject matter. I do know that chemistry can become confusing and that it's a challenging subject, but with a little work and effort, you can do a yeoman's job. Thank you.